What do you think? You do this one. Work on it. See if you can, all I ask is for the domain. Anybody want to tell me what the inequality is that I'm going to need to work with here? What do I need in order for this function to be defined? 9 minus x squared minus y squared greater than or equal. So this time it's okay to be equal, right? Because you can take the square root of 0. So that's what I'm working with. This again is a nonlinear inequality. Right? It's nonlinear. How in the world am I going to figure out what that looks like? Well, I like to go back again and go to the whole idea, the whole notion of we don't like inequalities, but equalities we're more comfortable with. So change this into an equality. This would be 9 minus x squared minus y squared equals 0, right? Anybody want to tell me what that is? It's a circle. Radius 3. Right, if we just move things around, right, that's a circle of radius 3. That's what it would be if it was equality, which we actually do have equality, right? So I'm going to draw myself a circle of radius 3. And I'm going to not make it dashed, right? It's going to be solid. That's supposed to be 3. Oops. Okay, that's my radius of 3 right there. The question is it the inside or the outside? So how can you check? Just test a point, 0, 0, right? Let's just test 0, 0 and check it into the original inequality. Is it true? Is 9 minus 0 squared minus 0 squared greater than 0? Yes. So it's everything inside, isn't it, since it worked? So when I draw this thing, right, when I graph this function, it should only exist above this circle, right? Outside that circle, there's no picture. You could also have taken this and worked with it as an inequality and recognized again that this is almost like the equation of a circle, right? But this is the biggest radius you can have, right? If these two squared together added up is less than or equal to 9, then it definitely would be less than or equal to 8, then 7, then 6, then 5, then 4, 3, 2, 1. You basically get all circles going down to 0. Understand? If you flip this inequality, what would it do? It'd be outside the circle, right? Okay. All right. All right, what about the range? This range is a little easier than the last one. Negative what? Negative 3 to 3? Is it possible to get negative 3 out of that function? When you take the square root of a number, can it ever be negative? No, not unless we're doing imaginary numbers, which we're not, right? So anytime you take the square root of a number, the smallest number you can ever get out would be what? 0, right? And then in this case, what would the biggest number you could get out be? 3. And that's because the largest that the argument could ever be, we also call this the radicand, the largest that this number could ever be would be 9. Why?
That's the only way we'll get it to work.
Yeah, but why do you know that this can't ever become 10 or 20? Because you're subtracting a number, right? Good. That is what? X squared is always a positive number. Y squared is always positive. So when you subtract a positive, it gets smaller, right? 9 is going to get smaller. If you subtract y squared again, it's going to get smaller. Now, you could have the situation where both x and y are 0, couldn't you? In that case, you would have 9 up there, right? If x and y are 0, you get 9. Yeah. So think about this. Above this, right? The biggest point you could get out, you just said, was 3. And it happened where? At the origin. So imagine coming out 3 units. 1, 2, 3. I've got a point. Now, what about right here if I plug in this point? That's the point 3, 0. What would come out? What would happen if you plug in 3, 0? You get 0. What if I plug in this point? 0. This one. This one. What do you think is going to happen at any point along here? You're going to get 0. So you've got the highest points here. All the edges are 0. You see what it looks like, right? You're showing me on the... There it is. Right? It's basically the upper hemisphere, isn't it? It's a surface. It's the top part of a sphere. I didn't answer the range. The range was what? 0 to 3. Questions? Now, that's when we have a function of 2 variables, right? Function of 2 variables. The input lives where? Function of 2 variables. Input lives in R2. Output is just a number, right? Yes?
Before we get off on that,
Yeah.
if we were to state the domain of that one, the circle,
Uh-huh.
would we write it as the inequality 9 minus x squared minus y squared greater than or equal to 0?
Or you can move things around either way.
Either way, as
But
long
that's-
as the statement is correct.
That's correct,
Yeah.
yes. Uh-huh. So we have input 2-dimensional space, output is 1 number, right? But there's nothing stopping us from going to a new function, f of x, y, z, where you have 3 inputs and a single output. But now we're starting to run out of letters, aren't we? Like, we just had just a second ago, z is f of x, y. But now I'm going to say, hey, look, my function's actually going to have x, y, and z. And so what do I call that, I'm out, like I ran out, z, right? So now you can start to use anything you want, right? I just, what? Huh? W, okay, I like W. There we go, W. So now you have, what this would require is an equation with 4 variables in it, where you could solve for one of them in terms of the other 3. If you're able to do that, you should get a, what would you get here? Well, you have 3 dimensions, right? 3 dimensions for the input, 1 dimension for the output. Can you visualize the domain? Will we be able to visualize the domain? Yes, it'll live in 3-dimensional space. But the range, the output, we can't put it together in the picture, can we? Because that would require a 4th dimension, right? Which means we can't visualize these, all right? Sometimes we call these hypersurfaces because it's like a 4th dimensional surface. But you can't see it. We can't actually show it to you. Understand? What we did just before this, we could see the domain and the range together in one picture. Not anymore for this. But we can still ask about domains. If I have a function of 3 variables, we can still very, very easily discuss domain. So let's do that. Here is a function of 3 variables. F of x, y, z equals square root. Very similar to what we just had, right? I don't know why this says A, A, B. It should be A, B, C. Was it A, B, B a while back too? Yeah. Well, I never get around to updating these things. All right. What do you get when you plug in 1, 2, 0? 4? Anyone disagree? Oh, root 4. Okay, root 4, which is 2. That okay? And then, what? Part B, domain. Uh-oh. We have a square root again, right? We need to make sure that the argument or the radicand, right, is not 0, or not negative, sorry. So we need that 9 minus x squared minus y squared minus z squared stay bigger than or equal to 0. What is that? That's a sphere, right? If we make that an equation, if we were to convert that into an equality instead of an inequality, we could rewrite that as 9 equals x squared plus y squared plus z squared. That's a sphere of radius 3, isn't it? But it's three-dimensional. So we've got this ball, right? Like that. Got this three-dimensional ball. And right now what we're saying is that the radius of this is 3, yeah? So that outside edge is this equation, just the outside surface. Are we allowed to plug in other points that are inside or outside of this? So will a point on the inside of this ball work? Well, what did we do before? We checked, didn't we? We tested. So why don't we test a point? Why don't we test the origin? 0, 0, 0. Does that work? So you come over here, you plug it into this. Does 0, 0 work? Yes, it does, which means you include the origin. So it's everything inside that ball. So this is it's a solid ball, isn't it? As opposed to just a surface. So this is a solid ball, radius 3. That's the domain, everyone. That's the domain. The range is nowhere to be seen, right? The range is nowhere on this picture. Understand? Let me give you a quick example before we say range. Well, I don't know. Range is pretty easy, isn't it? No? I need to quit saying that. It's easy, right? It's obvious. But it's very similar to the last problem, isn't it? What's the smallest that a square root can ever be? It'd be 0. Can you make this 0? Let x be 3, let y be 0, let y be 0, z be 0, right? Then you'll have 0. So you know you can get 0 to come out. The biggest that this thing could be is if it were just root 9, which you can do if it's 0, 0, 0. So you're going to get everything between 0 and 3 again. So the range of this is 0 to 3. What I was going to say before I did that was, let me give you an example of a useful function of 3 variables. We live on Earth, right? Like if we want to get really, really precise about it, isn't the gravitational acceleration, even though we say gravitational acceleration is constant on Earth, it does vary, doesn't it? It varies really with where you are. You change altitudes. You know, the gravitational force does change. It fluctuates. So you could say that the input is your x, y, and z on Earth, right? And the output is the actual gravitational force at that point. So the question would be, well, where are you allowed to talk about? Well, anywhere on Earth or inside of it, right? If you want to dig down 3 miles, the gravitational force is going to be different there. So your domain is this whole ball, right? The outputs is gravity at each of those points. So you pick me a point, plug it into some function, it's going to spit out the gravity at that point. Understand? I hope that makes sense. Another one would be temperature. Just think about the temperature in a room, right? The temperature in this room. Of course, if you look on the wall, there's a thermostat. But if we have a very precise instrument for measuring temperature, the temperature right here at this point is different than the temperature right here at this point, right? And so you could have the input is anything in this room, any point in this room, and the output is the temperature at that point. So you would have this function that takes in where you are and spits out the temperature at that. So these are actually very useful functions where your input's 3 variables. Okay. We're done with that one? Obviously, I don't have a picture of that function. All right, so your homework assignment. These are the homework assignments that I do want you to do. I have not put out the assignments for Chapter 11 yet on our website. So let's just go off of these. I'll write them on the board to the side so you have them. page 623, 1 through 12, and I put try the range. If you get hung up on range, don't worry too much about it. Moving on to 11.2. Well, if we're going to start talking about functions, then we're going to go back to Cal 1 again, and we're going to talk about limits, right? So, I mean, do you get that there's kind of a theme here? We started this out, we started talking about vectors, but then we said, hey, look, there's these things called vector functions, right? What do vector functions of one variable draw? So, like, what did the vector function r of t draw? Sometimes a line. Curves, right? Vector functions like r of t would draw a curve. Right? That might be in 2 space or in 3 space. Now we just talked about, all right, z is, oh wait, and when we did this, didn't we talk about derivatives, right? We talked about limits, we talked about derivatives, we talked about integrals, didn't we? Now what we're doing is we're looking at z as some function of 2 variables. We're saying that's a surface. And so what might, this is a function, it's a surface. What might come naturally now is, okay, well, let's talk about limits and continuity and derivatives and integrals of these, right? And what do they mean? That's where we're going. So the first thing is the limit. So for the limit, this is tricky. Remember from Cal 1 the definition of a limit. Remember this notation? Limit x goes to a of f of x equals a meant that as x got closer to a, the function got closer to L. So a picture of this is this right here. So here's some function. And what I'm going to do is I'm going to let my x values get closer to 0. So here I go. Notice the points on the graph, right? As my function gets closer, the x values get closer to 0. What is the function approaching? 1. Ah, shit. What happened? Well, because here's the function. The function is actually sine of x over x. Is it defined at 0? No, you can't plug 0 into this, can you? But the limit as you approach 0 is defined. It's getting closer to 1, obviously. We just can't actually let it go to 1, then the computer freaks out, right? So the limit was all about what was happening as you were getting close to a point. It had nothing to do with what was happening at the point, right? How is this going to work with a surface? Here's another example. Another function as we approach 0 from both sides. Look, if we come in from the left, what's my function approaching? 1. As we come in from the right, what is the function approaching? 0. See, so from the left side and from the right side, 2 different values. What would we say in this case? It's discontinuous. We'd say the limit does not exist, right? So what we needed in Cal 1 for the limit to exist is that from the left and the right, they had to go towards the same place, right? It was okay, for the limit, it was okay to have a hole as long as they both went to the same place, yes? But you had to check both from the left and the right, didn't you? All right, well, doesn't seem so bad. Important thing in two-dimensional space, the important thing was that the limit had to exist from both sides, all right? That was the main thing. Now, here's the actual notation that we use for limits with functions of 2 variables. See, when you were in a limit in Cal 1, x was approaching something, right? You were just approaching along the x-axis. But now, our function is a function of 2 variables. So your input is actually an ordered pair. So